Good afternoon, everyone. I'm very pleased to introduce today's De Giorgi colloquium speaker. Our speaker is Professor Volker Mehrmann from the Technical University in Berlin. Volker is long been a leading figure in applied mathematics, particularly in the fields of control theory, numerical analysis, differential equations, algebraic differential equations in particular, and mathematical modeling. So I promise not to take too much of his time. Just briefly, Volker received his PhD under Ludwig Elsner at the University of Bielefeld in 1982. He's held several positions in Aachen, Chemnitz, and since 2000, he's been professor at the Institute for Mathematics at the Technical University in Berlin. He has been one of the main figures in the creation of the Matheon, the research center in Berlin. He has been, from 2011 to 2013, the president of GAM, the German, the Society for Applied Mathematics and Mechanics, received ERC in 2011 for modeling, simulation, and control of multiphysics systems. From 2019 until just recently, the end of December, he was also president of the European Mathematical Society. He's a member of several academies. In 2015, he gave the Gauss Lecture. Among his awards, I'd like to mention is the WT and the Delia Reed Prize in Control in 2018 from SIAM, and the Hans Schneider Prize from the International Linear Algebra Society. His research deals with numerical linear algebra, differential algebraic equations, and control theory. He's the chief editor of Linear Algebra and its applications, and I believe a senior editor of Numerische Mathematik. These are very well-known journals in our field. Also, he is the author of several important books on topics like linear algebra, differential algebraic equations, and maybe Riccati equation. Do you have a book on the algebraic Riccati equations? And then last but not least, is the advisor of 36 now PhD students. So he's also a wonderful person to hang out with and a very good friend. I've known him for at least since the mid-90s. We couldn't quite agree exactly on what we met, but it's been a long time ago. And with that, please, Volker.
Yeah, thank you very much for the very, very nice introduction, and thank you very much for the invitation to the colloquium. It's a great pleasure to be here. I've always liked to be in Pisa and have lots of connections, including a PhD student called Riccardo Morandin, who is coming from Dario's group, and he will show up in the slides a couple of times. So what I want to talk about is in the last 5 or 6 years, it's really become an obsession. For me, it's energy-based modeling of multiphysics system. And Michele mentioned the ERC grant, and we wanted to do this, and in some sense in the beginning we miserably failed to do this in a proper way, and the reason was that we didn't have the right math. And so this is what I would like to talk about. So first of all, some general remarks. So I'm an applied mathematician, and if you look at modern key technologies, then what you have is that you have to model, simulate, optimize, or control really complex dynamical systems. Complex in many ways, complex because they're nonlinear, they are PDEs, but also complex because they require computational methods that are not all there. Most of these problems are multi-physics systems. I know there's only one physics, but meaning physics from different domains. Combining components from like electrical, mechanical, whatever. And they live on different scales. And they also have different modeling accuracies. And that's a real challenge. Modeling nowadays becomes exceedingly automatized. So people have designed modeling packages like Modelica. So where you can sit down at your screen, you click on a motor, it writes down the equations for you. It's really wonderful, but it puts all the challenges on the maths that you have to do in the background. So it writes down crazy equations, and then you have to work with them and analyze them. And in the future, one of the big topics at the moment, it's even in the hype cycle of American industry, is a so-called digital twins. So to have a digital model for every physical model that can run with the model for the lifetime. And in order to deal with all these things, I think we need to work more together in the math community between modelers, analysis, geometry, computational methods, and also data method. And my obsession is that I try to convince the mathematical community that they should do this to work together. So here's one of my favorite topics. So we have nowadays the energy sector, and in particular, since exactly 1 year ago, it has become a really important, even more important than we thought. That is, we have to couple different energy sectors. So there is all the green energy, wind and solar power, and then there's a classical sector like power plants with gas or coal or whatever, nuclear. And there's also nowadays, with all these electric cars, the transport sector. And this doesn't fit together. So at the moment, there are lots of obstacles that we have to overcome. So what are the challenges? So first of all, we all want our energy to come out of the socket. So the energy supply should be there. You have to couple different energy sectors, wind, solar, and they behave totally differently. Maybe not so much in Italy, but in Germany, the sun is not always shining so much as in Italy. They have different modeling accuracy, I mentioned then, and they live on different time scales. So the electrical system lives on a millisecond to second time scale, while gas has gas transport has a time scale of a bike. Roughly, that's a speed 15 meters per second. And we have to deal with increasing randomness, because the wind and solar power system becomes random, and decentralization. If everybody has a solar panel on the roof, that they are not only consumers of electricity, but also producers of energy. And so we need dynamical approaches. And at the moment, for example, the power system is completely stationary. It's run on a stationary model. Okay, so we need new mathematical approaches. And I will not talk about the power system. I will talk about the gas transport system, even though we've essentially stopped transporting a lot of gas, but it's much more developed, and also there are nicer partial differential equations there. So this is a joint research project, a big one, together with 5 universities, like such a center of excellence, which you could just acquired here, between Humboldt University, Technical University, University of Erlangen-Nuremberg, TU Darmstadt, and we get the data from an industry partner. It's Open Grid Europe, which is one of the biggest gas transport companies in Europe. So what is such a gas network? So a gas network is a network of partial differential equations with constraints. So you have these pipes, and on each pipe you have gas flow. And you have sources, so somebody pumps in a gas and it's transported. You have compressor stations because due to friction, the gas gets slower and slower, and then you use energy to increase the pressure. And you have the pipes, and you have valves, so it becomes discrete. You can close and open a valve. This continues, and yeah, and you have the consumers, which at the end have it in their household to heat. And you also have something else, which is to bring the modern world into the game. This is a compressor station. It's a huge building at the border between Germany and Czech. And what this whole thing does is nothing else than, based on certain parameters, it follows a curve. The curve for the pressure and the mass flow in the pipes. So it increases or decreases the flow. And then you have the network, the transport network. These are the big lines in Germany. Then each node in this is such a graph, and each node in this is another graph, and in each node of this is another graph. And so if you think about it, it's a really huge, complicated network. And on each of these nodes, there's a partial differential equation. Now you ask which partial differential equations. So the typical model that is used is a 1D Euler equations. Together with temperature. So you have mass conservation, rho is the density, t is time, so v is the velocity, so that's mass conservation. Then you have a momentum balance. This is a nonlinear equation. You have a friction term because the particles and at the walls you have friction, and that is a nonlinear term. You also have gravity coming into the game. So G is a gravitational constant, and H is the height of the pipe. Then you have the energy balance. And there the temperature comes in, and the heat transfer coefficient. Lambda is a friction coefficient. T is the temperature in the pipe, and TW is the wall temperature in the pipes. And you have the equation for the real gas. So this is a model, and in most applications, it's used 1D. But if you wanted to go 2025, we would have hydrogen. So a lot of the green energy produces green hydrogen, which in principle you could add into the gas networks. And then you would have to make sure that it doesn't demix. And then you would have to do it all in 3D. So the hydrogen and the methane doesn't mix. So this is a system of partial differential equation, which is on every node, plus all the other components. So we're getting worried, right? And actually what we are doing is we not only have the full model that I showed you, but we also have simplified models. So we have this so-called model hierarchy. So on top of the Euler equations, then we also have the isothermal Euler equations. We assume temperature is constant. We say that the space derivative of rho v squared and rho v cubed is small. So then we get to a slightly simplified model. We could assume that ddt rho v is small, simplified nonlinear equation. This is not done, by the way, by asymptotic analysis. It's just simplification by dropping terms. And you could look at the stationary model, and you could also say that this real gas factor is constant, and then you get a completely algebraic model. And then on top of all this sits an optimization method which uses discrete optimization, and they can't even deal with this algebraic equation. So it's approximated by piecewise linears. So this is a model hierarchy, and there's always a isothermal. And every element of node is is modeled via this hierarchy. So it's a PDE, one of these, and finite element, finite volume, or finite difference approximation in space, and then a time. And we also have reduced models. So if you are interested, there is a huge paper with all the details of all the equations and all the quantities in there, and it's permanently updated. So this model hierarchy is there. So it's a great playground. We're not only doing this gas transport, but we also look at district heating network. Then you have compressible Euler equations, which adds another difficulty. We also look at electrical circuits, power networks, electrical generators, and manufacturing repair of turbine blades, and brain models, and multi-body dynamics. And you look at this and you say, come on, what can you can't work in all these areas, right? The nice thing is the mathematics for all these can be put in one framework. And this is what I would like to talk about. So a couple of years ago, we sat in our coffee room and said, it was shortly before Christmas, and we said, let's make a wish list. What do we want our model class to look like? So we want it to be close to the physics, and it should be close to the physics for closed systems, so separate from the environment, and open systems. We want representation so that we can couple different parts over different physical domains. And the model class should have, I mean, we are mathematicians, we want to have nice algebraic, geometric, and analytical properties. And the model should be easy to analyze concerning existence, uniqueness, robustness, stability, uncertainty, errors, and so on. I started out as an algebraist, and I like normal forms, so I also added that we want to have a local invariance principles, and it should be good for discretization, so space discretization, time discretization, and we want to do simulation, control, and optimization. And the question is there such a jack of all trades? That's the English word. In German, we have a wonderful animal. It's called the eierlegende Wollmilchsau. It's an egg-laying wool milk saw. It's a perfect animal which gives you everything that you need. And so I like this word, and it fits very well to this. And so the basis of this general framework is energy-based modeling. And I think I don't have to tell many people here that variational principles based on energy is a fundamental principle. So the idea is to use energy and power as a lingua franca to couple different systems from different domains. So it's not certain variables, it's the energy that we use as a transport quantity. And this concept, which was roughly developed in 2000 from some engineering communities, splits our system into 3 different types. Energy storage, like a capacitance, a mass, that's a storage of energy. Energy dissipation components, like a resistor or friction in a pipe. Control inputs and outputs. And then you have to bring this together. And the thing to bring this together is a geometric framework. I will talk about this a little bit later in the talk. And in order to do what we want to do, we allow every component of the network to be a whole model hierarchy, one of these sets of partial differential equations that and then you take a systems theoretic point of view, which is not what we usually do in the mathematical world. And this gives you this so-called class of dissipative port-Hamiltonian systems. And I will give you 2 major viewpoints of this, a geometric one and a differential equation one, and I will show you how the 2 are interrelated. So a classical port-Hamiltonian system as it was defined in work by Arjan van der Schaft from Groningen. And there's a nice book here, a schism course that you can download, where this is all written up to model all these different components in this way. It has the following form. It's a nonlinear ODE, x dot equals j of x and t, and j describes the energy flux between storage elements, and j is skew symmetric, or skew Hermitian in the complex case. Then we have a minus r, and r is a positive semi-definite matrix function which describes energy loss or dissipation in the system. And then we have the gradient of an energy function, that's the Hamiltonian. And it describes the distribution of internal energy among the energy storage elements. So that's the classical Hamiltonian concept. And then on top of the classical Hamiltonian framework that we know from elementary courses in physics, you have ports. Ports are inputs, so U is input. And then in front of the ports, we have one time it's B minus P and the other time it's B plus P. And so the input and the output have the same dimension, and you may even have a term which goes directly from the input to the output that's split into its symmetric and skew symmetric part. So I wrote it down here in the ODE setting, but it could all these could be differential operators. Why is this a good class? So first of all, it generalizes classical Hamiltonian system, but it also generalizes gradient flow systems as we have in thermodynamics. The conservation of energy that you have in a classical Hamiltonian system is replaced by a dissipation inequality, that the Hamiltonian at time t1 minus that at time t0 is bounded from above by, that's why I need the equal dimension in the input and the output, by the inner product between the input and the output. And this is the so-called supplied energy. That's the energy that is brought in or taken out of a subcomponent. And the really nice thing is, if you take such a port-Hamiltonian system and you do a power-conserving interconnection, it's again a port-Hamiltonian system. So that you can now build Lego. You can build a component here, a component there, you interconnect them in a power-conserving way, and the resulting system has the same structure. So you gain the thing. A stability and passivity of such a system is also easy because typically the H is a Lyapunov function. So even in the nonlinear case, you have the Lyapunov function produced in the model. And you can do weak formulations, Galerkin projection, or model reduction via Galerkin, and it keeps the structure, which is really fantastic because that means when you go from infinite to finite dimension in a finite element or finite volume, you will still have the same. And the physical properties are encoded in the algebraic structure of these coefficients, so positive semi-definite and skew symmetry, and in the geometric structure of the flow, and I will come to this. I've been working on differential algebraic equations for many years, and the main important factor there is that you want to add constraints. Typical constraints are Kirchhoff's laws at nodes of networks, but they could also be position constraints for multi-body systems, or just continuity, or differentiability at nodes that you want to add. So I want to add those. And so when after we wrote the wish list together with my PhD student Ricardo Morandin, we extended this definition to a more general framework. And so now I have a matrix function E in front of x dot. So x is a state space, I is a time interval, and S is the Cartesian product of the two. So I still have this, But now I don't have the gradient of a Hamiltonian. I just have an arbitrary function E here. The rest is the same. And I have this term here. And this term is needed to do diffeomorphic transformations in time and space. So that comes into the game from transformation. I have a Hamiltonian. And these could be even rectangular matrix functions. So it doesn't even have to be square and nice. But we call this a port-Hamiltonian differential algebraic equation, or called short PHDAE, if 2 more or 4 more properties hold. So first of all, now we have a skew-symmetric function like we had in the classical Hamiltonian was a J, but this now includes the input and the output function. So this is skew-symmetric, and we have a dissipation function, which is W, which includes the classical dissipation part here, but also something coming from the input and from the feed-through term. So this matrix function is positive semi-definite locally. And we require that the gradient of the Hamiltonian is E transpose, where E is this factor here, times this E term. So if E is the identity, then little e is gradient of the Hamiltonian, then we are in the previous case, but we don't need that. And that the time derivative is the inner product of this E and R, and you will see in a minute why I need this. This is an extra term. So it looks a little bit more ugly. On the other hand, all the framework that was there in the classical port-Hamiltonian is still there. So what are the properties of PHDAs? So even with a singular E, even E could even, the big matrix E could even be 0. So we had a stationary problem that fits into this framework. So the first thing is you get a power balance equation and the dissipation inequality, despite the fact that you added these constraints. So the total time derivative of the Hamiltonian is given by this function here, because W is positive semi-definite, this is negative semi-definite, plus Y transpose U. So that's the dissipated energy, that is this part, and the supplied energy, which is the part that I had before. And if you make use of the fact that this is positive negative semi-definite, you get this dissipation inequality when you integrate it. So it's the same as before. So that is nice. You want to do interconnection. So you can make, first of all, make these systems autonomous without destroying the structure. So you introduce T dot equals 1 as an extra equation, add it to the system, and then you get that. I didn't put it on a slide. So if you take 2 such systems, and you take U to be both inputs and Y to be both outputs, and you make any, at the moment we still assume linear relation between the inputs and the outputs, then the total interconnected system has the same structure, and the Hamiltonians, the energy function, is just added. If you have a nonlinear function here, that's relation between the Hamiltonians will be a bit more complicated. And this was the theorem that took us the longest time. So if you take another state space and you do a diffeomorphism, a local diffeomorphism, that maps the state to the new state, and you multiply the equations with a pointwise invertible matrix, then what you get is, again, a port-Hamiltonian DAE. And so here are all the formulas. And then you need this R term that is dealing with time-varying transformations. So you can write down the transformation. It's not nice, but you can locally apply diffeomorphism, and you get this. And furthermore, if this is a global diffeomorphism, then the 2 systems are equivalent in the sense that one can be transformed into the other. So it's a different coordinate system can be chosen to maybe get nicer properties from. And you can construct local normal forms using such transformation. Okay, So that's the differential equation point of view. Now, what is the geometric point of view? So a huge group of people in this field look at it from a geometric point of view. And so let F be a linear space of dimension n. Can also be done in infinite dimension, but I write it down here in the finite dimension, and E to be the dual space. And then I define two bilinear forms, the one with a plus and the one with a minus. And the one with the plus adds an E from the dual space and an F from the F2 plus E2 times F1. And the one with the minus has this with a negative sign. And a linear subspace of this F Cartesian product with E is called a Dirac structure if this plus form is 0 on D, and D is maximal with respect to the property. What is a typical example? The most simple example is just the symplectic matrix 0 identity minus identity 0, which defines such a form, and the E and the F are the two parts. Or the PQ representation of mechanical systems would give you that. That's where it comes from. And then there is a Lagrange structure or Lagrange subspace. It's if this minus form is 0. And the Lagrange structure we also need in a negative version. That's to describe the dissipation. And so it's called negative if the quadratic form associated with this is non-negative on the Lagrange structure. So that's, and then you can make an abstract definition of this stuff that I wrote down in a differential equation in the following way. So I have linear spaces, a state space X, a space of resistive flows. These are the flows which are run through a resistor or dissipating. A space of external flows, these are the ports, and you take their dual spaces. And then such a Dirac structure looks like this. It's a Cartesian product of X and its dual, the ports and its dual, and the resistive part and its dual. And the Lagrange structure, which describes, so this describes power transportation from one part of the system, or energy transportation from one part to the other. And the non-negative Lagrange structure is just a part of this resistive system here that describes energy dissipation. And abstractly, you could write such a port-Hamiltonian system like this. It's X dot X, FP, EP, FR, ER. There exists something in the dual formulation such that XX star is Lagrangian and FR, ER is resistive. So this is a way of writing it with relations and with form. And this can also be done in the nonlinear case with a modulated structure so that the functions depend on the state, and then you get what I wrote down there before in the differential equation framework. So how can we view this? So we have the storage elements, and between the storage and the Dirac structure or the routing structure, there are these E's and F's. They're called efforts and flows in the geometric modeling community for such systems. This comes out of bond graph theory, which was very popular in the 70s. And there are the resistive efforts and flows, and then the port effort and flows. And so this is how you build the system. There's always components, and you interconnect them with such a geometric structure. And that you do in a Lego-like fashion. So let's recap this. This was the definition that I had before. Same definition. And now, how are they related? So you can show that given an autonomous PHDAE in this form, you define the flow fiber, which is the storage fiber, the port fiber, and the resistive fiber for all x, where the flow fiber is described by E of x times, so I don't have a t because it's autonomous, is the tangent space at x. That's the storage fiber. The same thing for the port flow fiber and the resistive fiber. Then you divide your F, your flows, into these three components, and your E's into these three components. And then the corresponding Dirac structure associated with the differential equation that I wrote down, there is all these F and E, which live in Vx and cross Vx star, which satisfy such a relation. And you see here, gamma is skew-symmetric. You have a skew-symmetric matrix which maps the F's into the E's. And this is a Dirac structure, and you define Fs to be Exx minus Exx dot, Es to be Ex, Fp to be Y, Ep to be U, and Er to be minus W times Fr. And then you get exactly the differential equation framework. And this inner product between the effort and the flow, this is really the power balance equation. So you have this geometric framework, you can translate it into the differential equation framework, and the physics in the background is all there. So then you want to go to PDEs. Now, there are different ways to do this. So first of all, you could just say, okay, these matrices are now operators, linear or nonlinear operators, and that's one way. Then there is, in the thermodynamic community, there's a thing called generic. This is gradient flow systems, would give you a different way. You could also look at formal Dirac structures to make this formal setting, or you could look at structured PDE systems with inputs and outputs. And I can provide the slides, so there is references. So in the linear case, it would look like something like this. You have a generalized state variable Z, you have operators J and R, and you have the gradient of the Hamilton function, and you have an input operator and an output operator, which is a formal dual, and they are operators. So J is skew-joint, R is self-adjoint semi-elliptic, and the input and the output are connected in this way. And E of Z is the relative energy, which is only conserved quantity. It's the only a conserved quantity, and there's no if there's no dissipation and no entropy. And if you want to do thermodynamics, you have to incorporate entropy equations. So there's some work how to rewrite this. So now let's go back to our Euler equations in the gas transport. Are they port-Hamiltonian in this framework? No. Why not? Well, between Euler and what is now used in gas transport, people have been dropping terms. So these red terms, which is the pressure, energy, and the dissipation work, is usually not considered. But they give you the symmetries. So if you leave them out, the nice symmetry structure is destroyed. And also you need to add an equation for the entropy balance. So if you write it like this, you can prove that fits into this framework perfectly nice. We have to add node conditions, so for the interconnection, and boundary condition. And the boundary conditions, I will talk about this in a second. The boundary conditions are a problem. So there is no uniform way to deal with the boundary conditions. So classically in PDEs, we want the boundary conditions to make sure that our system is well posed, that we get a unique solution or things like that. Here, the boundary conditions also should reflect this geometry and this symmetry structure. So, for example, in the gas flow model, the wall temperature boundary condition, so this temperature at the outside, that could be a classical boundary condition for the PDE, or it could be that I want to interconnect with the environment because all these pipes heat up the environment, and then it would be an interconnection variable. So this is different. And the inflow and outflow boundary conditions, they're controls and observations, but they can also be used for interconnection if you have two pipes that come together, and then you put a continuity condition there. Let me go to space and time discretization. And space discretization is surprisingly easy. You do whatever you do for your PDEs anyway, finite elements, weak formulations. Galerkin keeps the structure. So that's easy. But you could also, that is currently a hot topic, use exterior calculus. So go to the representation in forms and use the Rahmen cohomology. And the hard part is, again, the boundary conditions, that you get them right in this framework. That's what we are currently working on together with Andrea Brugnoli, who is a postdoc at the moment. But there are also hybrid approaches which mix this exterior calculus and the classical framework. I'm not going to talk about this part, but it's much easier than the time discretization. The time discretization is so difficult because most classical ODE or DAE methods do not preserve the energy or the dissipation inequality. So you need something like symplectic methods to keep the geometry. But unfortunately, to preserve the Dirac structure, you would have to use some symplectic methods. And to preserve the constraints, you would have to use something which is called stiffly accurate methods. And there is no symplectic stiffly accurate method, time discretization method. So you have to do something special. That's Ricardo working on in his PhD thesis, which hopefully soon is on the out. And then one result is there's no implicit Runge-Kutta discretization that is both stiffly accurate and symplectic, which is bad news. Otherwise, if there were one, we would use that one, and that's it. So you can use either partitioned Runge-Kutta methods or Galerkin methods. Gauss-Legendre collocation method, like the implicit midpoint rule, would be good, and a stiffly accurate method for the algebraic part. So how do you deal with the fact that you have these boundary conditions? Well, you do write it in such a way that the discrete system in time also satisfies a power balance equation. So you write down the Dirac structure, and you require it at the grid points in your time grid. So you make sure that at each time point you have this geometric structure with the flows, efforts, and then you write down the usual formulas for collocation methods. And when you do that, then what you get is, on the discrete level, at every point you get this, that the derivative of this function h of t, which is h of x of t, that this satisfies this equation here, which is, again, the inner product between the input and the output at the endpoint, and the resistive part, which is this positive semi-definite part, which is encoded in this term. And then you can show that if you apply a collocation method, then you would get that this satisfies the power balance equation except for the discretization error. So in this last term, you could have trouble, because if the discretization has the wrong sign in this O of HP plus 1 term, then you could get a little bit of dissipation or gain a little bit of energy. But if you use the Runge-Kutta method with positive coefficients, then you really get that this is less than or equal to 0. And if the Hamiltonian is quadratic, then it's even exact. So that's also nice. I can't resist to put in a little bit, does it help us anything for the linear algebra? And the answer is, when you do space-time discretization method, you get a nonlinear system or linear system. And it's a large-scale problem if it's a discretized PDE. And does the PHDAE structure help? So here's an example, which is topical for everything. So if you discretize this with the implicit midpoint rule, you get such a linear system that you have to solve. Remember, E was positive semi-definite. That was the Hessian of the Hamiltonian. R is positive semi-definite. So this is a positive semi-definite matrix. And then you have a skew-symmetric part. And the skew-symmetric part has a time discretization parameter in front of it. So that's typically small. So locally, the structure and in Newton's method always leads to linear systems with a semi-definite symmetric part. So question, does that help us anything? It's very similar to what you get in saddle point structures from. So I was very proud of this result, and then I found out it wasn't new. So, so if you have systems that can be split into symmetric and skew-symmetric part, where the symmetric part is positive definite, if this is the case, then you can multiply with M inverse, the equation, and then the equation looks like this. It's identity minus a matrix which is skew-symmetric in the inner product given by the M. And this is exactly the structure that for so-called Krylov subspace methods, it gives you the optimal three-term recurrence relation and a Galerkin condition for the residual. And there's a lot of work in Michele and Golub and Liesen paper, but we put it together also for the case that M is semi-definite. But the original work is by Olaf Wittlund from Courant Institute in 1978. And it's completely forgotten. It's hardly ever cited, this method, and it gives you a great method. So here's an example. This is Stokes' equation. These are the runtimes. If you run Wittlund's method, this is what you get with the classical non-symmetric generalized minimal residual solver. Here we get an accuracy of 10 to the minus 9, and here it's 10 to the minus 2. You need 10 iteration and 500 iteration. It gets better if the step size is smaller. So if you get more accurate in space and time, then the iterative method gets better because the skew-symmetric part is getting smaller. So, and here's some convergence plot. You can see how much faster it is compared to these are for different step sizes, 0.001. So 5 iteration here was 10. If you make the step size smaller, it's even faster. So, and to come to the end, we've been using all this machinery now in the gas transport. And so we do a little bit more than the usual space-time adaptive methods that you use in numerics. We also add now the model. So we allow that you can switch up the model, going to 1D Euler or going to simplified models. We go to space discretization, finer or coarser, and time discretization, finer and coarser. We have determined all the sensitivities when you go from one model to the other. So we have a factor there that we can use in the error estimation. And then you choose a cost function or an adaptation strategy and use this adaptivity to drive the simulation or optimization methods. And the system theoretic approach allows you to jump between the models. So inside every node, there's a model hierarchy, but the outside doesn't see it. It sees the same inputs and outputs, and it doesn't see which model you're using. And then you can make the system faster. So here is a 4-model hierarchy. That's the simplest one I wanted to put on the slide. So the full model is the isothermal Euler equations, would be this set of partial differential equation. Then in the next level, we drop the gravitation term because we are in northern Germany. It's flat anyway, so don't have to worry about gravitation. Second model is you drop this rho v squared ddx rho v squared term, and model 3 is a stationary model. So then we build a cost function. This is a cost function for the computational cost. So we take the error estimator for the model error, the error estimator for the space discretization error, the error estimator for the time discretization error, and we want this scaled by the number of components to be less than or equal to the tolerance. And when we did this and put this into a flow solver, we dropped it from 4 hours to 80% less, so 20%, which is some minutes. And we also used it to optimize the cost of the compressor. So the compressor, it takes gas out of the transport network, heats up or he brings up the pressure, and that is a cost. I mean, our industrial partner says we never look at this. It's negligible, but it was a very nice cost function. So we optimized this, and so you can see. So D is a discretization, omega D is a discretization error. This is a stationary model. M is a modeling error, and eta is a total error. And so you can play with the errors. So you say, oops, you want to go to 10 to the minus 3. Then you do 2 switching in the model and 4 switchings in the discretization. These are real models from the industry partner, that these gas lip models. And what are the conclusions from that? And actually, we could solve optimizations problems that never could be solved before with this method. So what about our wish list? I mean, there's a lot of things to be done, but in a way, with the port-Hamiltonian DAE systems, you can get close to answering all the wish points. So it's like Christmas. So that's why I like it very much. I'm very enthusiastic about it. But there are lots of things to do. For example, real-time control. All this uses high-performance computing to do this. If you want to do this in real time in a power system network, you have half a second to do the control. And half a second, then you better cook down the model as much as possible so that you can do the solutions. We don't really know how to put uncertainty and stochastics into the model nicely. We have already worked on delay, and that because after all, you need some time to calculate the control, and that takes some delay in the time, and that is delay equations. The right function spaces, actually, we're going for the RAM cohomology. We're going for these geometric stuff because there the function spaces are well, but we don't know whether this really is the best possible way. Error estimates, we are working on this preconditioning for the linear systems. And a big topic right now is data-based. So in many cases, like this compressor station, we never will model this. We just have input-output data, flow, mass flow, and velocity in, mass flow, and velocity out. We would like to have a port-Hamiltonian model for this. And we know how to do this, but the model that comes out is so lousy, we can't use it. And we're putting it in digital twin together with a Siemens factory. We have been building this. Okay, so with this, I would like to thank you for your attention and my sponsors for the support. Thanks a lot.
Thank you, Volker, for a very comprehensive presentation of this large area of applied mathematics. I'd like to know if there are any questions or comments from the audience. Dario.
Very nice and interesting. Well, can you comment about the computational challenges here? That is, I would like to know if the matrices involved in these models are huge or small, or do they have any structure like semi-separable tuplets or something like that?
Unfortunately, I haven't looked at semi-separable and tuplets, but they are sparse and they are large. And because you take the boundary conditions to the outside, they are usually much sparser than the ones that you get from finite elements directly, because this solution at the boundary where you insert the boundary conditions is not done. It's in the input and the outputs. So depending on what you do with the model, you have sparser matrices. They are essentially whatever your operator is. If this is a Laplace operator, then it looks like the discretization of a Laplace operator. So there's nothing new really on the space discretization. Because you have DAEs, you always have to do implicit methods. And because you have to do implicit methods, you have to run Newton's method. And you better write it in such a way that the matrices that you get in Newton's method are also nicely and sparse in structure. That is extra challenge to do. So computationally, I would say there's nothing else to be done than in classical PDE modeling for Euler equations. I wouldn't see any extra effort that is needed. The only thing you get is these extra positive semi-definiteness of the matrices. So that's the structure we partially know how to exploit, but there's work to be done, like in saddle point problems in general. This challenge with the time discretization is a pain. I mean, I must say. Other than that, I wouldn't see any extra challenge.
Thank you.
Are there any other questions for Volker? Comments?
I wanted to ask about the port-Hamiltonian equations.
Yep.
So you say usually some terms in the fluid equations are neglected.
Yes.
Do they have small coefficients, or
They do have small coefficients, but if you neglect them, you should also neglect the corresponding symmetric pair partners. So this is a wide open problem. We had a semantic semester on this topic 2 years ago, and I asked my colleagues who do asymptotic analysis, can you do it in a geometrically sound way so that you really combine this with asymptotic analysis, so that when you do expansions and look at small terms and scale them, that you get them at the same time. And in some parts we can do it, but in general, I don't have a machinery that tells it. This is really done by the engineers in the past. Oh, this term is ugly, just drop it. It's small. We do experiments, we see it's small, it's only 10 to the minus 1. And that's not good. So that really destroys the structure.
Yeah.
But we have one example. I mentioned pore elasticity. They're funny. So this is a model which is really a second order model, but it has rho times the second time derivative. And rho, the density is low. So if you look at the quasi-stationary limit that is usually considered, this second order term is gone and it's not port-Hamiltonian anymore. If you go back to Biot's original modeling, the second order term is there. So you keep it because it's second order. You go to first order, you add the velocity as an extra term, it's port-Hamiltonian, and then you can drop it there and you get this kind of structure. So what I'm saying is, in the classical modeling approaches that we see, it pays a lot of good if you go back to the original models and don't look at what the engineers give you, what they have been using the last 10 years in their classical engineering framework. And actually, in most cases, the old guys, 50 or 70 years ago, they came from a Hamiltonian point of view and they had it right. So it's just, this is the world that we are living in. This is a model that is everybody is using, but that doesn't mean that it's a good model.
Okay, thank you.
I'm going to ask a quick one. So you mentioned a couple of times the RAM cohomology, which may not be obvious to everyone. What it has to do with this. Is this used in the same sense as Doug Arnold's approach?
Yes, it's exactly the same. There you have this, the diff operator, the grad operator. You have all the, they put them in such a framework, and then you have the right function Sobolev spaces for each of these
kernels and images.
Kernels and images, and then you have one form, 0 forms, 1 forms, 2 forms, 3 forms, and so on. And you write everything like this. You can write in this framework. The only difference that I see is how you treat the boundary conditions. So at the moment with Andrea Brugnoli, my postdoc, we are looking at this from the point of view, how do you have to do the boundary condition in such a way that they fit into this framework? And it turns out the way to do it is a primal dual, it's a variational formulation comes into play, and it's a primal dual formulation where you always get 2 variables, the primal variables, the e's of dual variables, the f's, and they fit them together nicely and everything fits.
And the idea is to have a discrete complex that mimics exactly the behavior of the continuous one with projections.
Yes, and so that you can use it in control and in simulation, which is usually in the stuff that Doug Arnold and the other people, and also the colleagues here in Pavia and in APFL, they're just solving the PDE. They're not looking at the control problem around. So that's the difference.
Any other questions or comments before we thank Volker? If not, well, thank you, Volker.
You're welcome.